Okay, so this is part 2. This is going to be on an emitter follower. Okay, and the emitter follower is a stage that doesn't have gain. Well, it has a gain of 1, I should say. And its biggest goal is it has a couple of jobs that it can do. One is shifting a voltage down by VB on or a VT, VB on for BJT. The other job that it does nicely is that it shows a very small R out, but a high R in. So let's draw it first. Okay, so and we'll just tie that to the supply. Okay, and here's your V in, and here's your V out. Okay, remember when you name these things, you look at where V in and V out are connected, and whatever's left, you call this a common whatever's left. And right here the collector is left over, so this is a common collector, but because it's used as a buffer, in other words, the output follows the input by just this difference in voltage right here, this VB on right here. So if V in goes up by a volt, V out goes up by a volt. They're just separated by VB on. Because of that, they call this a follower. Okay, an emitter follower. Okay, not much different. Doesn't matter what circuit you're analyzing, you still goes through the same steps. So if you want to know how much V out moves when V in moves, or you want to find the R out of the circuit or the R in of the circuit, first thing you do is you set all the let's start a new Word document. First thing you do is you set DC sources to, let's move this over here. First thing you do is you set DC sources to, let's move the circuit over here. Okay. So there's your circuit, and first thing you do is you set DC sources to ground. So you want every source. Again, V in is a source, V supply is a source, but for our analysis, our small signal analysis, you only want to keep the moving sources. So there's that. Okay. Okay, and then to do the small signal analysis, you need to replace your transistor with that small signal model, which we have over here. Instead of having me draw it again, actually, it's probably easier to go over to this one. Where's my Word document? Okay. There's your small signal model, and what you want to do is lost the new one. There's your small signal model. What you want to do is take this transistor and replace it with this in this circuit. Okay, so what we see here is here's our transistor, basically base emitter collector. Here's base emitter collector. You can see that the collector is connected to ground, so we can just tie that to ground. All right, the emitter is connected to V out. And then the emitter is also connected to a resistor that goes to ground. And the base is connected to V in. Okay, so there's our circuit that we're going to work with. before any simplifications or anything. That's what our circuit looks like. Okay, now just to make analysis a little bit easier, we can put things in parallel if there's stuff that goes in parallel, or get rid of things if there's stuff we can get rid of. Right now, we see that we have a resistor right here going from V out to ground. So RO goes from V out to ground. You also have this resistor right here, which I didn't label, that goes from V out to ground. Okay, so these two, they're both going from this node to ground, so they are in parallel. So let's label that. I didn't label that over here. So let's call this just R. So this is just R. And now we can take that and now we can take that R and it just goes in parallel with RO. So let's see, should we kind of didn't leave myself drawing space, so let's just move that down a little bit, and then we can do this is in parallel with R, and now we can get rid of that. Okay, and our resulting circuit, get rid of some of the X's and all. And our resulting circuit is that. Okay, and put that in there since that's prettier than the other ones. Okay, let's do some math. Let's get equation from over here. Should we do, which one's going to be easiest? Let's do GM since we didn't do it last time. Okay, let's do GM. So GM, I'm using a big GM to represent, it's the GM for the entire circuit, and that means we look at I out versus V in. And since we, when you use lowercase right here, that means that it's the moving signal. It's already got this delta inside of it. So that's what we have there. That's what we're looking for. We're looking for an equation of I out over V in equals something. So let's go back and mark I out on here. So I out is going to be going out of that. And we already have V in. Okay. Let's go. So let's do a little more work here. Since it's not completely easily obvious, first step we want to do is come up with an equation that relates I out and V in. Okay, let's find an equation for I out. Okay, I out equals the current coming from this direction, from this direction, from this direction. Okay, so let's look at the current going across RO in parallel with R. That would be this node minus this node. So 0 minus V out over that resistance, which is RO in parallel with R. So that's the current coming down this branch. Current coming down that branch is nice because it's already written out. It's GM VBE. Okay. Plus, so that's the current going down this branch. The current going down that branch, again, isn't the prettiest equation. V in minus V out. Okay, so the voltage across there is V in on this side and V out on that side. And then, oh, I forgot to put in the R pi again. That's R pi. Oh. R pi. Okay, so this doesn't look like it's got some things in there that we really don't want in our final equation. The only currents and voltages we have in our equation for GM are I out and V in. So anything that's not I out or V in, we need to get rid of it in this equation. Okay, so I see, oh, goodness gracious. Sorry, skipping steps again. Okay, the two-port rule for this, which makes things very nice, is if you're trying to find GM, what you have is you set V out equal to 0. You'll see it in books as RL equals 0. That just means that there's no resistor between the output and ground. So there's V out equals 0. Okay, going back over here for GM, if V out equals 0, that makes sense. You got a ground on this side, ground on this side. This term right here disappears. Okay, let's add some more information here. So V out equals 0. Other things we know. What about VBE? Now that V out equals 0, VBE equals V in minus 0, which equals V in. All right, and now let's see. When we rewrite this equation, so V out goes to 0, so this goes away. That's okay, because in our equation up here, let's see, we only want I out and V in. So this term goes away, so that's nice. We know that VBE is just a V in. Okay, and now we have an equation that the only currents and voltages that are in it are the ones in our original equation right here. Okay, so to get this equation right here, I want to divide both sides by V in. So let's do that. If you divide both sides by V in, it disappears from here and disappears from here. And that is what GM equals. Okay, I'm going to be back in just a flash. Where'd it go? Where'd it go? See that displayed? Hopefully that's what you can see. Alright, so that's your GM. Remember, gain is GM times R out. So let's find R out now. Let's go back to paint number 2. Okay, so for GM, we set this equal to ground. Okay, now we want to find R out. So the two-port rule for R out is that you set V in equal to 0 and do your math. So let's do that now. that there. And let's put this one for your GM. Okay, that's for GM. I can make that a little bit smaller now that we're done with it. Okay, and okay, so now what we want to find, okay, what we want to find is R out, and R out equals V out over I out with V in equal to 0. And so what we actually have is I'm thinking I have a typo up above, so let's go check up above. Did I make a mistake here? I out over V in? Nope, that's right. Okay. So this is what we're looking for. So our first goal is to, since it's not immediately clear what R out is, we have to set up an equation, and we have I out. I like to start with a current. If there's a current in this equation, I generally like to set that current equal to something and do KCL. Okay, so I out, that equals the current across here. And now that V out isn't ground, we can't ignore this. So that is equal to, oh, went away. Shrink this a little bit. So I out, the current through here is 0 minus V out. So minus V out over RO parallel with R plus current through there. So we have the same thing we did last time before we did the simplification. VBE, and then plus the current through R pi right here that I keep forgetting to draw in on the picture, but that is V in minus V out, but V in equals to 0. So again, this is a negative V out over R pi. Okay, so to find this, to find what we're trying to do here is find an equation and set it so that one side of the equal sign is V out over I out, and then that equals, and then the equation for V out over I out. So we want to get rid of everything, every voltage or current that isn't V out or I out, and we have this VBE here. So let's figure out what, oops, there it goes. Let's figure out what VBE is. So VBE is from here to here. And you can see that 0 minus V out. So VBE just equals negative V out. Okay, replacing that back in this equation, and we'll end up on the next page. Replacing V out with VBE with negative V out means you have this. Okay. So everything's negative there. And what we need V out over I out. So what we're going to do is let's factor out V out from that side. So we have V out times, okay, let's take this whole thing, V out times, we factored a V out of the first term, factored a V out of the second term, and factored a V out, oops, of the third term, and that's what we get. do I have I out in the correct definition? We're having a minus sign issue here, I think. Okay, and final thing that we want to see is V out over I out. And so if you divide both sides by this messy thing right here, and then divide both sides by I out, let's get this so we can see it again, we get a sign issue, but you get, on one side, you get 1 over this whole thing, and that equals your V out over I out. Okay. Let me go back and see where my sign issue is. Okay. The good news is all of the signs agree, which is one thing you need. But these should all be positive. Okay, I will figure that out by tomorrow. Really, it's something awfully basic, like I out signs wrong. I out. Equals I out. All right, well, I'll figure that out by tomorrow. Okay, but this equation right here, these actually should be positive. One thing that's interesting here, GM, the units of GM, that's a 1 over a resistance. Okay, Siemens is 1 over resistance. So you've got 1 over resistance plus 1 over resistance plus 1 over resistance. This whole thing is negated, but if you factor out the minus sign, you get 1 over resistance, 1 over resistance, 1 over resistance. If you remember, that is the equation of resistors in parallel. Okay, so it's taking, it's looking at this and this and this as in parallel, which makes sense. They all go from this node to ground. All right, so okay, okay. As I said, I'll fix this later. But from the last set of slides, you know that gain is change in V out over change in V in. But you can also do that by multiplying change in I out over V in, which is GM, times change in V out over I out, which is R out. So GM times R out. We just figured out R out here, and we just figured out GM here. Okay, so GM is GM, big GM is GM, little GM plus R pi. So big GM, the GM of the entire circuit, is the GM of that transistor plus 1 over R pi. So let's go over here for a second and steal this one. So we know R out. Which is equal to that. We know GM equals little gm plus 1 over R pi. Okay, and just because I know that this should be positive, if you look at this, it's R pi here. GM, we're seeing, 0.2, 0.1, 0.02 or something. This R pi here, we've seen 1K, 2K, something like that. So this right here is actually quite a bit smaller than this GM. And if you really want to hand wave, you can say that, yeah, 1 over r pi, it's so small, we can just call that GM. Okay. Now let's look at r out. R out. So here we've got GM. We've got the same thing going on here, and down here we just ignored 1 over r pi. We've got GM plus 1 over r pi. Right? And if you assume that r is on the order of r pi, remember RO is going to be pretty darn big compared to r. And because it's so big, this just looks like 1 over r. These two right here are going to be much smaller than GM, and you can approximate this as, with my sign error, as 1 over GM. Okay, that means your gain, AV equals big GM times R out, which equals GM times, with the sign error, yeah, whatever. Okay, try it one more time, and that equals 1, -1 in this case, but it should be 1. So you can see that the gain of the follower is I mean, this is the right answer right there. The gain is about 1, and so whatever signal comes in, however much the input signal changes, the output changes by the same amount. In other words, it's doing the exact same thing. I'll leave that sign in there so I can fix my math later. And the other thing that you notice is 1 over GM, if GM is 0.2, then now R out is like 5 ohms. Okay? And that's what you want. You want a really low R out. So the good thing about this follower is it gives you the same signal in, since the gain is 1, gives you the same signal out as in. Might be shifted a little bit, but it gives you the same signal out as it receives. But it shows a very large R out. Okay. The last thing that's important here is, okay, so now what we can do is we have this circuit here. We have our amplifier with a big R out, and it goes into this follower, which shows a low R out. That's great. That's exactly what we want. Now we're getting the same signal here as we get here. It's just that the R out looks low here, but it looks big here. Okay. So that's great. The way to get the same signal here as here is you don't want your output stage, you don't want the follower here to load your amplifier. So what you need here is a big R in. You want a giant R in, so it doesn't load your amplifier. So let's look at what you need to do there. Okay. So you want a big R in, so let's go find the R in for the follower. Well, actually, I've got a picture down here, so R in can be a little bit messier, because you don't get to, the two-port model lets you simplify some things in your diagram. So we want to get rid of this, because it's not ground anymore, because we're not doing GM. So for R in, we don't get to use any, there's no two-port rules that simplify things, so we have to just use the complete model. And there's CR, okay, Yeah, this can actually get quite messy. So what I'm going to do is I'm going to show you a shortcut. And we'll actually go back to, do we have that on here? No. So we're going to go back and we're going to return this. We're not going to take this out of parallel. Take this out of parallel. And then we're going to add that resistor back. It's supposed to be an R. And the other thing I want to put here is that there's some voltage at this node. It's V out. We'll call it Vx for the heck of it. It is V out. Grab this. Alright. So now I returned it to the original picture. I'm going to actually get rid of this one. Alright. And now we want to find Rn. Whoop, it looks like YouTube is finished downloading. Nope, 98. Okay, so let's find Rn. Rn is V in or I in, but unfortunately you don't get to do anything here. That disappears. Okay, which means V in I in. Okay, so that's the way you would have to go about finding the equation for Rn. The trick here is you have some voltage at this node, and that voltage comes from, what color should we use here? Purple. That voltage comes from some IB coming through this way, IB coming through this way, and some IC kind of coming from, so these two branches combine and give you IC. Okay, so the total current through this resistor right here is IB plus IC. Okay, these two currents right here, this IC is coming and combining back down and recombining here, so you have IC coming from these two branches and IB coming from that. Okay, so what you have here is you have Vx equals IB. Be much faster to do it in the other thing, but IC, this whole thing times R. Okay, so now I'm going to ask you a question. Okay. How can I keep, oops, it's still doing something. It's processing it. Okay. Question is, how can I keep Vx on this node but get rid of this whole side? Right, so going back over here, let's get rid of this. Okay, I want to keep Vx over here, but I want to keep Vx over here, but let's say, just to make the math simpler, I want to get rid of this whole side here. I want to keep Vx the same, but I want to get rid of all this nasty circuit stuff to make my calculations easier. Okay. Right now, if I just get rid of it all, now I used to have IB plus IC going through here, so I used to have a bigger current going through here, but now I've gotten rid of IC. Now Vx, it's not going to be the same voltage as before. Okay, so let's go a little farther with this math here. Okay, you know that IC is just beta IB. So let's do IB plus beta IB times R. Okay, but what the current that's actually coming through here is IB. So let's factor out an IB here. So I'll say IB times 1 plus beta R. Okay, so let's see what this is saying. This is saying if I passed IB through a resistor of size R times 1 plus beta, I'd get Vx. Okay, so if I pass IB plus IC through a resistor of size R, I get Vx. But just going through the math here, this thing right here will still equal Vx. But what you can see is if I had a resistor of size R times 1 plus beta, and I had a current of IB through that resistor, I'd still get Vx. Okay, so what you can do is, now this is no longer the same circuit as we had before, but if you had a resistor of size R times 1 plus beta, got a resistor of size R times 1 plus beta, now you'd have Vx back again. Okay. This is going way too fast, and I wish I had a whole nother lecture to talk about this and let you ask questions. Now you can see if you are sitting on Vn and you try to push some current through there, all you see are two resistors in series. Okay, and the two resistors in series are, so R in, just see two resistors in series, that's R pi, that's not a pi, R pi plus R times 1 plus beta. And that's your shortcut. Instead of doing the whole circuit analysis, you can say, well, if I only have IB current through here instead of IB plus IC, and I need this voltage to be the same, I need to make the resistor bigger. By how much? This math tells us that we need to increase this resistor by a multiplier of 1 plus beta. Now if we put IB through this resistor, we get our Vx back. And then if this is a resistor of R times 1 plus beta, now we just have two resistors in series. If you're sitting over there trying to push current through there, you see R pi plus R times 1 plus beta. That's the shortcut. And now you have an equation right here for the Rn of the follower. Okay, so the second half of your lab is how you can increase Rn. So remember, we've got your amplifier here, and you're putting an output stage. Now you have your amplifier, the output of your amplifier goes into this output stage, and we're using a follower here. And we want this follower not to load the amplifier, so we need to have a really high Rn here. Okay. So the second half of your lab is to somehow increase the Rn of your follower so it doesn't load your amplifier. Okay, that was way too much information, way too quickly, but I hope that at least will give you a first view of these circuits. Ask lots of questions tomorrow, and I will post I will post these 2 documents that I drew up along with the video. Okay, but the video is taking a heck of a long time. This is taking longer than expected. Your video has been queued and will be processed as soon as possible. Okay, so I'll get this all posted up as soon as I can.